this video, I'm going to show you how to graph a rational function. Now, it's very similar to graphing a polynomial function. There's only one more thing you have to look at, and that is the asymptotes, both vertical and horizontal. But we'll start with the first step, which is looking at your intercepts. X-intercepts will occur whenever f of x equals 0. So you'll take that function, set it equal to 0. Now with a rational function, what you'll need to do is factor both the numerator and the denominator. Make sure there's no common factors, which there are not. And now we can just look at the numerator. Whenever the numerator is 0, the function will be equal to 0. Which means x equals 1 and x equals minus 1 are x intercepts. We'll look at the y-intercept. Which will occur when x is equal to 0 or at f at 0, which would be 0 squared minus 1 over 0 squared minus 4, which is 1 over 4. So therefore, the y-intercept is 1 over 4. Now we'll look at the asymptotes, and there's going to be two potential asymptotes, a vertical and a horizontal. So the vertical asymptote occurs when the denominator of the rational is equal to 0. And in this case, that would mean x squared minus 4 is equal to 0, or x will be equal to plus or minus 2, which will be our vertical asymptotes. And then you'll look at your horizontal asymptote. Now I'm not going to require you to work this out in detail. It's enough that you remember the rule. If you have a function, a rational function, you can just look at the degree of the numerator and denominator. If the degrees are equal, which they are in this case, then you just look at the leading coefficient of those two terms, which is 1 in both cases, and the horizontal asymptote will be the quotient of these two things, which is 1. So there is a horizontal asymptote of y equal 1. Okay, so that's it for looking at f at x. Next thing you're going to have to do is calculate the derivative in order to get the intervals of increase and decrease in the max and. Now with a rational, working out the derivative is going to be a little bit more complicated than a polynomial. You'll have to use the quotient rule. I've already worked it out, so I'm just going to write it down, but you would have to use the quotient rule to figure this out. But for the sake of time and space, this is the first derivative. So we'll try to figure out the critical numbers, which is whenever this is equal to 0, which would be when the numerator equals 0, or x equals 0 is a critical number. So now we're going to set up a first derivative test. So we have our intervals. So we're going to have to include our critical number in the interval, but we also have to include the numbers where the function or the derivative is undefined, which is at plus and minus 2. So we're going to go from minus infinity to minus 2, minus 2 to 0, 0 to 2, and then 2 to infinity. And we are looking at the first derivative here, so we just want the sign of the first derivative in these intervals. So if x is in this interval here, the first derivative would be positive. Between minus 2 and 0 would be positive. Positive. Between 0 and 2, you'd be negative, and between 2 and infinity, you would be negative. So we have increasing, increasing, decreasing, decreasing. So f of x is increasing if x is between minus infinity and minus 2, or minus 2 to 0. Now don't combine these intervals because remember the function's undefined at 2. And decreasing if x is between 0 and 2, or 2 to infinity. Again, don't combine those intervals because the function is undefined at 2. So that's our intervals of increase and decrease. Now we want the max and min. There is only one. There's a maximum when x equals 0 because it changes from increasing to decreasing. So we'll need to evaluate the function at 0. We already did that, right? That was the y-intercept. So we know the y-intercept is 1 over 4. So if at 0 is 1 over 4, and that turns out to be a maximum, or at least a local maximum value. So therefore, there is a local maximum at 0, 1 over 4. The next thing you're going to want to look at is intervals of concavity. So for that, you're going to have to calculate the second derivative, which would require calculating the derivative of the first derivative, which again would require using the quotient rule. So I've already done that. That is equal to 6 times 3x squared plus 4 all over x squared minus 4 to the power of 3. Now if you go to do this, you'll notice I've actually simplified this quite a bit. So you want to simplify these derivatives as much as you can because you will need to factor them and try to figure out where they're equal to 0. So the simpler they are, the easier that will be. Notice this one. What we would do now is set this equal to 0. But the numerator here is never equal to 0, so this is never true. So for no values of x. So what that tells me is there's not going to be any points of inflection. But I still need to do my concavity test because I need to figure out if it is concave up or concave down. And even though there's no values where f double prime at x is equal to 0, it is still undefined at 2 and minus 2. So my interval table needs to include minus 2 and 2. Now if there was no zeros and no points where it was undefined, you would just look at the entire interval from minus infinity to infinity and try to figure out if it was concave up or concave down. So now I'm looking at the second derivative, trying to figure out if this would be positive in these three intervals. So between minus infinity and minus 2, this would be a positive number. Between minus 2 and 0, this would be a negative number. And bigger than 2, we'd have a positive. So we're concave up, concave down, and concave up. So therefore, f at x is concave up if x is in the interval from minus infinity to minus 2, or 2 to infinity, and concave down if x is between minus 2 and 2. And then the last one, points of inflection, we said there are no points of inflection. Now notice the graph does change from concave up to down and then back to up at minus 2 and 2, but those are not points of inflection because the function is actually undefined at these values, minus 2 and 2. Okay, and then the last step is to graph the function. So draw your axes. And you'll have to graph all key points. So remember our x-intercepts were plus and minus 1. Our y-intercept was 1 over 4. We had a maximum value or maximum point at 0, 1 over 4. And the other thing you can add to these graphs is a vertical asymptote. Or asymptote at plus and minus 2, and a horizontal asymptote of y equals 1. So now we'll put all these things on the graph. So we need to come up with a scale. So my y scale, I've got the vertical asymptote of 1, so I want that to be on my graph. And the other key y value is 1/4, so that would be 1/4 of the way there. Key x values are 1, minus 1, 2, minus 2. So come up with a scale that allows me to graph that. So this is 1, this would be minus 1. So at 2, x equals 2, I have a vertical asymptote. X equals minus 2, I have a vertical asymptote. And then y equals 1, minus 1 were intercepts. And then, sorry, x equals 1 and minus 1 were x-intercepts. And then y equals 1/4, be right about there, was a y-intercept. Okay, so now I need to kind of graph this function. So I'll graph between minus 2 and 2. That should be the easiest portion of the graph. So notice it was concave down between minus 2 and 2. So I'm concave down, And if you look at the intervals of increase and decrease, it started increasing till I got to 0 and then decreased. So it would have to look like that and approach the asymptotes in this way. Now there's the portion over here between, well, from minus infinity to minus 2 and from 2 to infinity. That's a little bit trickier because there's no key points. There's no points to actually graph in these intervals. But if we look from minus infinity to 2, our concavity was up, so we should be concave up, and we were increasing. So I need to be concave up, so that's curving this way, and increasing, so going up. And then I'm going to have to approach the horizontal asymptote on the one side and the vertical asymptote on the other. So it must look something like this. And then over here, so from 2 to infinity, we're concave up and decreasing. So concave up and decreasing, and then it has to approach these asymptotes. So it would look something like that. So this rational function is going to look something like this, and that's how you graph a rational function.